We've introduced ordinary least squares, regression lines. We've done a regression by hand. We talked about the assumptions necessary to run a regression, an appropriate regression. And now let's introduce two measures of fit, the goodness of fit. How well does this regression line fit our data? The R-squared and the standard error of regression. A natural question is, how well does the regression line fit or explain the data? This lecture introduces the two measures, R-squared and the standard error of regression. So to estimate the R-squared, we need to talk about these three different values: the total sum of squares, the TSS, which is a measure of the total sample variation, or how spread out the yi are in the sample. Okay, so you're probably getting used to seeing sums of squares at this point. So we've got the sum and we've got a square. We're going to be talking about three different sums of squares here. The total sum of squares is the difference between each data point, the yi, and the sample average, each of those values squared and then summed up. That's the total sum of squares, the total variation in the data. The explained sum of squares, the second here, the ESS, is a measure of explained variation in the predicted values, the y hats. So here the difference is, instead of finding the difference or the distance between each data point and the sample average, we're going to find the difference between, or the distance between, each predicted value, the y hats, and the sample average, and then square that and then sum it. And then the residual sum of squares, or the SSR, is a measure of unexplained variation, the UI. Note that the UI hat, the sum of the UI hats are equal to 0 by construction. That was assumption number 1 from the previous lecture. But here we're talking about the sum of the UI hats squared. So a quick note, each yi is equal to the predicted y plus the residual. So how we can put in the definition of the y hat. It's going to be beta hat 0 plus beta hat 1 xi. And so we're just basically putting in this predicted value here and giving sort of a definition. The data points are equal to the predicted values plus the residuals. This implies that the sample variation in y in the data points is equal to the sample variation in the predicted y's plus the sample variation in the residuals, which implies the total sum of squares from the previous slide is equal to the explained sum of squares plus the residual sum of squares. And we can use these values to construct something useful, the R-squared. The R-squared is the ratio of the explained sum of squares over the total sum of squares. So by construction, the explained sum of squares has to be less than the total sum of squares, because the predicted values are going to be closer, well, they're on the line relative to, they're on the regression line, where the data points are not on the regression line. So the variation in the explained values has to be less than the variation in the data points values, the total sum of squares. So this thing is going to be less than or equal to 1. This is also, we can use the residual sum of squares, and just by rearranging, this is equal to 1 minus the residual sum of squares over the total sum of squares. Some interpretations of the R-squared. It's the ratio of explained by the regression equation variation compared to the total variation. In other words, if the regression equation explains a lot of the variation, this thing is going to be closer to 1, meaning 100% of the variation is explained by the regression equation. It's a fraction of sample variation in y that is explained by x, or how much of y is explained by x. So if there's some amount of variation in y, what percentage of that variation is explained by x? The R-squared is contained in the interval 0 to 1, so R-squared is greater than or equal to 0 and less than or equal to 1. R-squared of 1 means that the x perfectly predicts y. All the variation in y can be explained by x. R squared of 0 means that x does not explain any of the variation in y. In practice, we never get an R squared of 0 or 1, but these are sort of like perfect correlation and zero correlation, not possible to have. Is a high R squared necessarily good? Well, it's good in the sense that the x is doing a good job at predicting the y, but it doesn't tell us anything about a causal relationship between x and y. We could just have systematic bias. It's predictable, sometimes positive, sometimes negative, but cancels out. We can think of an approximate straight line fitting a CDF. So, in other words, a high R squared tells us we're doing a good job of predicting the y, but it doesn't really tell us anything about the relationship between x and y, whether or not they're causal, if the assumptions of the of OLS hold or not. Let's introduce the standard error of regression. It's an estimator of the standard deviation of the regression error UI. Because UI are unobserved, these are not UI hats, these are the population errors. We use the sample counterpart, the UI hats, the OLS residuals. The standard error of regression is equal to the square root of the standard deviation of the residuals. So, or the standard, sorry, the variance of the residuals. So this is the standard deviation of the residuals. This is the variance of the residuals because it has a squared, and then we're going to take the square root of it to get the standard deviation. The formula is written here. It's going to be 1 over n minus 2. The minus 2 is a correction for degrees of freedom. We're estimating the regression with 2 degrees of freedom, beta hat 0 and beta hat 1. And we're summing up over all the UI, the residuals minus their means, the sample averages, and then squaring those values. And note that by construction, the sample average of the residuals is equal to 0, so that bit drops out and we're left with the final equation here. So it's almost like the average of the residuals squared, but not quite because of the degree of freedom correction. The standard error of regression, the units are the residuals are the same as the yi, so that's nice. It's the same units as our dependent variable. SER is a measure of the spread of the observations around the regression line. It measures average size of OLS residuals or average mistake made by the OLS regression line. We already talked about why we divide by n minus 2. Let's do an example of these values. So the book gives us the regression equation of test scores related to student-teacher ratios, and this is what we get. And suppose this results in an R squared value of 0.05 and a standard error of regression of 18.6. This regression says that student-teacher ratios explains only 5% of the variation in test scores. That's this value here. In other words, our x variable, student-teacher ratios, is only explaining 5% of the variation in test scores. If we were to write this down, R squared equals explain sum of squares over total sum of squares. And so let's say the total sum of squares of in this case was equal to 100, and then the explained sum of squares would be equal to 5. That's what we're doing here. 5% of the variation in the total sum of squares, or the y variable, is explained by the x variable. That means that 95% of the variation in test scores is left unexplained. This is not surprising. There's a lot of other information that we needed to explain wages, like ability or income in the neighborhood, or what the test is on, maybe. One thing to note is that this doesn't say that student-teacher ratios is not an important variable. It just says that there's a lot of other information that's left out of this equation, what's contained in the residuals or the error term. Okay, let's do an example of R squared. So this is the same example we did when we ran the regression by hand, except now we're going to estimate the r squared. Okay, let me write in here, what was our beta 0 hat from this one? Beta 0 hat, when we did this regression by hand, was equal to $2.85 per hour, and beta 1 hat was equal to 0.714. All right, so what we're doing here is we're getting the predicted YIs, the predicted wages, by taking beta 0 hat for each of these observations. We're going to take beta 0 hat 285 plus 0.714 plus the intercept here times each xi. So for the first line, we're multiplying by 1 because education in the first line is equal to 1. For the second line, we would just do the same thing, but we'll put in 2 because the second observation for education is equal to 2, and the predicted wages are for each of those in those boxes there. The residuals are going to be the y hats minus the yi's, so that's going to be this 3.564. I have this written backwards, obviously. This is yi minus y hat because of the negative here. So we're going 3 minus 3.564, which equals negative 0.564, and then we do that for every observation. The residual squared is just the squared value of each of the things in this fourth column here. And then we can sum up all the residuals squared to get 0.8574. The yi minus y bar squared, that's what we have in this column, and the sum of that is equal to 8. And then the y hat I minus the y bar squared, for the final column, the sum of that is 7.137. Okay, so this is the explained sum of squares, this is the total sum of squares. We can figure out what the r squared is going to be. It's going to be 7.137 over 8. I have these on the next slide. And then let's catch up where we were, 7.137 over 8. So the r squared is 0.8921. This is the fraction of the sample variation in y. The sample variation in y was wages. That is explained by x, education. So how much of y is explained by x? This says that approximately 89% of the variation in y is explained by x. That's quite a lot. That means, though, that 11% is still unexplained. What could explain it? Maybe ability. Why would we want it to be high? Why would we want the r squared to be high? Well, we want our regression line to fit our data. That seems fairly obvious. But what could we use it for? If our regression line is fitting our data well, then we can be confident that we can predict out of sample well. This could be useful if you're trying to make a prediction about what maybe some commodity price will be in the future. If you're going to buy a futures contract, you want to know what the commodity price will be in the future, and you can use a regression to do that. The standard error regression, okay, we calculated the u hat I squared in this table over here. That's this column here that I'm circling. It was 0.8574, and we're going to plug that in to this equation here for the sum of the u hat I squared. And then we multiply it by 1 over n minus 2, where n is 4, because there's 4 observations, and then we take the square root, and we're left with 0.654. This is the average size of the OLS residual. The average size, when we're talking about the residuals, we're talking about, here's the data points, right? So if we have a couple data points, we have the predicted values that fall in the line, and the residuals are the difference. I'm going to put hats over those. And the standard error regression is telling us what's the average size of those residuals. It's the average mistake of OLS in predicting the data points. It's in units of the y variable, so it's in units of dollars per hour. So the average mistake is about 0.65 cents. or on average, the OLS regression makes a 65 cent per hour mistake in predicting wages.